Hello everyone. In this class we will begin with symmetry and group theory. Without the basics of symmetry we just cannot understand group theory, and before entering into the symmetry we will also discuss some basics that are related to the symmetry. So if at all we understand what exactly is symmetry, now we can have some questions. Why are we studying symmetry in chemistry? Because usually whenever we say symmetry, it looks like a mathematical concept. There is a math involved in symmetry, but here we are using the same mathematical concept to understand chemistry. We are aware that chemistry and mathematics are intricately related. So without mathematics, we just cannot understand chemistry at its deepest levels. Now when it comes to the meaning of symmetry, what exactly is meaning of symmetry? So whenever we ask this simple question to any general student, the answer that we get is symmetry is anything related to the presence of plane, presence or absence of plane. Anything that has a plane is symmetric and anything that do not have a plane is unsymmetric. That is a general conception of an average student. I mean, wherever you go, you just get the same answer. Yes, to some extent it is true, because whichever object that we find, whatever we see in the nature, at very first instance we will try to see whether it is symmetric or not with respect to that plane. Now suppose if I look at this board, at a very first instance when we look at the board, we say that it is looking symmetric. On what basis that we say it is looking symmetric? Suppose if I am passing a plane, one half is a reflection of the other half, or the same plane if I pass in a different coordinates, again one half will be the reflection of another half. So just by imagining this reflection or a plane of symmetry, we say that one particular object is looking symmetric or the other particular object may not be looking symmetric, right? But that exactly is not the concept. Plane is only one of the symmetry elements with which you are able to define a particular object. Suppose if I am looking at this same board, it is not just the plane that defines the symmetry present in it, but along with the plane we also have some other symmetry elements with which we can measure what is the symmetry present in it. Measure in the sense all these are imaginary things. Okay. So why am I saying measure? When it comes to the word symmetry, we can just break it into sim and metry, where sim refer to similarness or repeatedness, and metry is related to measurement. What are we trying to measure in a particular given entity is the similarness or the repeatedness or a particular pattern that is present in the given entity. So for our discussion purpose, I can just take any monument, whether you can take a Taj Mahal or you can take Charminar or Lotus Temple or any other monuments that are built. Whatever is present in the nature, you can choose a plant, you can choose any animal, or you can choose any insect, any fly. Whatever things that we choose, we try to find a particular pattern present in its construction. Now we are not going to analyze those patterns, but we are going to apply that same symmetry for our chemical entities. So whenever I say chemical entity, this entity could be an atom, it could be a molecule, or it could be any subatomic particle. It could be an atom, molecule, subatomic particle, and so on and so forth. So what exactly is the symmetry present in all these atom, molecule or subatomic particles we have to analyze, and all such things we are calling it as an entity, chemical entity. So whenever I use a terminology called as entity, it could be related to an atom, molecule or any other subatomic particle, but mostly we have to study the symmetry of the molecules. Atom, it is very easy to visualize because atom is considered to be spherical, but molecules will have different shapes and geometries. So this particular symmetry is more applicable to the molecules. Okay. See, we need not go to the basics, how the universe is formed, all those things. It is present in other videos, basics. But just to understand, according to the theories, universe is made up of two things. One is the matter, and the other one, it is the forces that will keep the matter intact. So matter and forces. This matter or forces, they are made up of something which have spin. So we are not speaking about the forces, it is not our part. Suppose if I consider matter, this matter is made up of either protons, neutrons, electrons. All these are spin half particles. Whether I take a proton or I take a neutron or I take an electron, all these are spin half particles, or you say spin 1/2 particles. Now if I particularly consider a proton or a neutron, whether a proton or a neutron is further made up of 3 quarks. Three quarks make up a proton, 3 quarks make up a neutron, and the spin of this quark is also found to be 1/2. So when it comes to the conclusion, all matter is made up of other particles whose spin is 1/2, whether it is a quark, 3 quarks make up a proton or 3 quarks make up a neutron. The spin of a proton or a neutron is also 1/2, and the spin of an electron is also 1/2. Here we are not speaking about the charge. Charge is different from the spin, right? This is not about the charge, it is about the spin. So these are spin 1/2 particles. Even the quarks that make up the protons and neutrons are spin 1/2 particles. So to understand what is the spin, I am saying that these subatomic particles have a spin of 1/2. What is this spin of 1/2? Okay. Or if I consider the forces, these forces are made up of some other particles whose spin could be either 0, 1 or 2, right? So how do I get 0, 1 or 2, or how do I get a spin of 1/2 and so on? All this can be understood from the symmetry. Now, I will just give a small example. Suppose I give you some molecule, say let me take a water molecule, because this is one of the basic examples. So we always start with a water molecule, one of the very basic example taken in the symmetry. Whenever we give a molecule, to understand the symmetry of any particular given chemical entity, right? I am choosing a molecule here, the entity is a molecule. The molecule has an oxygen and 2 hydrogens attached to it. So I want to understand the symmetry of this particular water molecule. Then immediately a question arises, Why should I study the symmetry? Why should I study the symmetry of this molecule? What is the purpose of studying the symmetry? Is there any use for it? Then the answer is, it is because once I study the symmetry of this water molecule, once I understand what is the pattern that is present in the given molecule, then I can understand some properties also. So the answer is, some properties can be understood. What kind of properties can be understood? So mostly these are qualitative, not quantitative. Just let me give an example. Suppose I give you water molecule, I'll ask you whether the molecule is polar or not, or I may ask you whether it is optically active or not. Then the regular convention is you just go and put it in an instrument and then you measure whether it is rotating or not, whether it is rotating the plane polarized light or not. If at all it is able to rotate the plane polarized light, then you say it is optically active. Or if it is not able to rotate the plane polarized light, you say it is optically inactive. Also you can measure how much is the rotation. Okay, all that is quantitative, whether it is plus 15 or minus 15, all that is quantitative. But just by looking at the molecule, if I want to say whether it is optically active or inactive, or just by looking at the molecule, whether I can say it is polar or not, that can be done with the help of symmetry. So if I know what is the symmetry of a particular molecule, I can just say whether it is optically active or not. I can say whether it is polar or not, or I can say whether it is having any stereoisomer or not. If at all stereoisomer is present, how many number of stereoisomers are present? That can also be understood. And not just these things, suppose if I can understand the symmetry of any particular given molecule, we can also understand the spectroscopic properties. We can also understand the spectroscopic properties. Just for example, we may choose IR and Raman. So I can understand what are the infrared spectroscopic properties of a given molecule, or the Raman spectroscopic properties of a given molecule. How many vibrations are present in a given molecule? Is that particular vibration IR active or Raman active? All these things can be understood just by knowing the symmetry of that particular molecule. Not just this, we can also understand what is the hybridization present in a given molecule. So if I give you PCl5 or I may give you H2O, NH3, what hybridization is present you can understand from the symmetry. In that hybridization, which particular orbital is involved can also be understood. Suppose if there are 4 hybrid orbitals involved, out of these 4 hybrid orbitals, is it sp3 hybridized or is it dsp2 hybridized? If it is dsp2, what is that d orbital, right? Or I may choose sp3d. If I have sp3d orbital, I mean sp3d hybridization, what is the d orbital? Is it dz square or is it dx square minus y square? All those things can be understood just by knowing the symmetry of a particular molecule. So that is the importance of the symmetry, right? Every one of us might get a doubt, why should I study symmetry? Because this symmetry we are relating it to a group theory. As I said, symmetry is a mathematical concept which we are applying to chemistry. So there is also something called as a group theory which is related to mathematics. And once you apply the symmetry group theory, you can understand the spectroscopic properties, some qualitative properties such as dipole moment or the polarity or optical activity, hybridization, which hybrid orbital is involved, and what is the orientation of that particular orbital, in which direction is it oriented. All that information can be brought about just by knowing the symmetry of a particular molecule. Okay. Right. Now just getting to the next step, when I say that we have to study the symmetry of a given molecule, so most of the times I take the chemical entity as a molecule, because every time atom do not change, the atom is considered to be spherical, so the shape or the structure do not change a lot. Then we have to go to the molecule. If I say water molecule, that has a particular structure, or if I take ammonia, that has a different structure. So when I choose a different molecule, the structures also change. Symmetry properties can also change. We have millions of molecules, right? And all these millions of molecules, we can just put them into some groups. If I have, say, one molecule, second, third, fourth or fifth molecules are given, I may put them into one group, or all these 5 molecules may belong to 5 different groups. So to which group does it belong? That depends on the symmetry present in it. Once I can understand the symmetry, then I measure what is the symmetry present in it, I gather all the symmetry, then I take it as a group. That we call it as a point group. That will take some time. We have to understand all the basics, only then we have to enter. Now first important point is to understand symmetry. This particular concept of symmetry is purely imaginary. It is purely imaginary. Whenever I say that plane is present, I give you a water molecule, I say there is a plane that can bisect the molecule into symmetrical halves. That do not directly bisect the molecule, but it is our imagination that we are imagining a plane, and that particular plane is bisecting a given entity into symmetrical halves. I say the board is symmetric. Then you have to imagine a plane which is bisecting the board into symmetrical halves that are mirror images to each other. So imagination is highly important for understanding symmetry. Without imagination, symmetry cannot be understood. A lot of concentration has to be put in this particular topic, because most of the inorganic topics you are aware of, these are theoretical concepts. But when it comes to the symmetry, it is mostly applicative. Second thing, it is mostly imaginary. So without imagination, you just cannot apply. Okay. If you are able to imagine just few things, you can just apply it even to millions of the molecules. I give you millions of molecules. Just by knowing the basics of symmetry, you can say what is its point group. Once you understand what is its point group, you can construct a character table. Once you construct a character table, all the spectroscopic properties, hybridization, everything will come into your viewpoint. Okay. So I'll give you those basics, how to understand this symmetry. Whatever space that we are present in, this space, all this space is defined by 3 dimensions. So we call it as a 3-dimensional space. This is a 3-dimensional space. You simply call it as a 3D. And these 3 dimensions, these can be given in the form of coordinates. So we are defining these 3 dimensions in the form of coordinates. These we refer as Cartesian coordinates. Three spatial coordinates, or you can just define it by Cartesian coordinates. What are these Cartesian coordinates? We take them as x, y and z. So this 3-dimensional space we are trying to define in the form of 3 Cartesian coordinates, and we are defining it in the x, y and z coordinates. Once we are able to understand this x, y and z coordinates, it will become very easy to know the symmetry of a given molecule. How are these x, y and z coordinates aligned? Now before showing any model, I just request you to imagine with your fingers, right? Suppose if I am showing my right hand, put the fingers in such a way that one is pointing towards you, one is pointing towards your right and left, and one to top and bottom. I am showing only one. If this is the point that is considered, if this is the center point, then one half is towards you. You have to imagine the other half is away from you. From that point, one half is towards your right, the other half will be towards your left. From this point, one half is above, the other half will be below. Okay. So this I call it as plus coordinate, minus coordinate, minus coordinate, plus coordinate and a minus coordinate. Okay. So whenever we hold the fingers in this way, I mean whenever we are showing the fingers in this way, this by convention is taken as x axis and this by convention is taken as y. This is taken as z. Okay, this is, as I say, it is a convention. So it is for our convenience to understand, I have taken this as x, y and z. Now whatever molecule that I say, you try to find out the symmetry, you have to imagine the molecule, put the orientation in such a way that it falls in these spatial coordinates. Then you can simply operate some symmetry elements, you will understand the symmetry of that particular molecule. Okay. So I am just representing it again, x, y and z. The same thing I will draw it here. This will make it as z, the one pointing towards you as x, minus x, y and minus y. So these are the three spatial coordinates. So how do I define a particular point? Whatever point that we choose in this space has 3 degrees of freedom. We say any point in a space enjoys 3 degrees of freedom. From your infrared spectroscopy basics, you might know it is defined by 3n, that we define it as a 3 degrees of freedom. So whatever molecule that we choose has 3 degrees of freedom, and what are these 3 degrees of freedom? These are 3 into n. So that could be translation, rotational, vibrational, all those things. Okay. But in this case, whenever I say in a particular given space, how do I move? It is not about the vibration, right? It is not about the rotation, but in a particular given space, suppose if I am present in this space, then what are the various ways that I move? I have only 3 possibilities. The first possibility is, suppose if I am standing here. Now from this point, I can just move towards my front or back. Or to simply say, with respect to a student, I can move towards you, I can move away from you. So this is 1 degree of freedom that I enjoy, right? It is not a rotation, it is not a vibration, it is a translation. Now what is the other way that I move? I can move this way. So I can move towards your right, or I can also move towards your left, right? So one movement is towards you and it is away from you. One is towards your right and one is towards your left, and I can move above or below. It is just like top to bottom. This is the third movement. So in space I can move in 3 different directions. One is this way, towards you and away from you, towards your right and left, right, and up and down, or top and bottom. So these are the only 3 ways that you can move in the space, and all these 3 ways are defined by 3 particular coordinates. So when I am moving top to bottom, this is along z axis. This convention you have to remember. This is z axis, top and bottom, or up and down. X towards you and away from you, and y towards your right and left, towards your right and left. That is x, y and z coordinates. Okay. Why we are defining all these coordinates is whatever symmetry elements that we have, which we use to measure a particular symmetry present in a molecule, all those things have to be imagined in the purview of these coordinates x, y and z. Okay. Now let me give a small example. Suppose if there is a medical doctor, he want to do some surgery, he just want to operate, and for doing some operation he definitely requires some equipment. Suppose if I give scissors to a medical doctor for performing any surgery or an operation, with the help of scissors he tries to cut the skin, okay, or he tries to cut some part of the body. Suppose if I give him a needle, then he tries to sew. Okay. So whenever a needle is given, he tries to sew, or whenever a scissors is given, he will try to cut. All these are equipment provided for a medical doctor so that he can perform a surgery or an operation. Likewise, suppose if I give you a molecule, in this particular molecule, suppose if I am showing you a molecular model of a H2O, oxygen and 2 hydrogens are present. Right? I will ask you what is the symmetry present in this. Then as a chemist or as a student of chemistry, what we do is we have to do some operation on this, and all this operation is purely imaginary. Right? So for performing this operation we also require some equipment, just as a doctor require a scalpel, or he may require a needle or a scissors. In a similar way we also require some equipment, and these equipment we call them as elements. Right? So these are the elements used to measure the symmetry present in a given molecule. For that reason we say these are symmetry elements. So once I provide any student for chemistry, if I provide him or her, if I provide some symmetry elements, then he or she will be able to operate on this particular molecule with the given set of symmetry elements. Then whatever particular symmetry element that is present in the molecule, you have to put it in a group. And once you make it as a group, you assign the name for it. Suppose it could be a C2V point group or a C3V D2H, then you assign a name for it. Once you assign, you construct a character table, and from the character table you try to get all the data related to this molecule. This is a very long process, but since it is a beginning class, we will only discuss some basics related to this symmetry. Okay. So what I said is, to understand symmetry we require something called as elements. These elements we define as symmetry elements. Okay. How many symmetry elements are present? Then a general convention is, some say 4 symmetry elements, some say 5 symmetry elements, but the basic number of symmetry elements that are present to define the symmetry of any given molecule, these are 3. 3 basic symmetry elements. And what are these 3 basic symmetry elements? The first one is an axis, second is a plane, and third is a point. So axis, if I just put this, it is taken as a line. Over this line, if I show some rotation, then we call it as a symmetry axis. This rotation is an operation, but to indicate that as an axis we show this rotation. Okay, but that rotation comes under operation. Axis is an element. If I simply put this, it is generally considered as a line. This is not a line, it is an axis. Or you may also take an arrow then you may show this. So this is a better convention, because when I just put this, it is considered as a line. When I put an arrow, it is just considered as an axis. Over that axis, we can show a particular rotation. And once I am showing a rotation, it is considered as an operation. So if you are confused with an operation in the beginning, then you need not show this. If you are aware of symmetry, then you can show, but if you are a basic student, if you are trying to understand the basic, then you can just remove this. So once you have removed this, this is considered as an axis. That axis could be along z axis, z direction, or it could be along x, or it could be along y. The next one is a plane. So this is one plane. It is just an xz plane, or instead of putting a complete plane, you may just take half of it. This is just half a plane. You need not show the complete one, you can just take a half of it. So either you can represent it this way or this way. This is taken as another symmetry element. The first symmetry element is an axis. Whenever you are showing this curly arrow, it will show the rotation, which is an operation. Both are intricately related, but for your basic purpose, if you can show this arrow, that is more than enough. That represents an axis. This or this will represent a plane. And the third basic one is a point. These are the three basic symmetry elements. Okay. Axis, plane, and a point. So for your easy remembrance, just as your smartphones has many apps, our symmetry also has this app. Okay, you can just try to remember in that way. What is the app for this symmetry? Is axis, plane, and a point. With these three symmetry elements, you can generate some other symmetry elements also. Now, whenever I am operating on a particular molecule, I may choose one or more than one of these symmetry elements. Supposing that I am choosing axis as well as a plane, both elements I am choosing, then that will generate another symmetry element, which is called as the improper axis of rotation or alternating axis of rotation, where the axis will be alternated by a plane or a plane will be alternated by a axis. So the combination of this axis and a plane can generate a fourth symmetry element, which we call it as a improper axis of symmetry, or you may call it as alternating axis of symmetry. That is counted as a fourth symmetry element. But basically we have three. One is axis, second one is a plane, and third one is a point. Combination of two elements, axis and a plane, is giving you a fourth element called as alternating axis of symmetry, or you can also call it as improper axis of symmetry. And all the symmetry elements will be defined by some Mulliken symbolism. We will discuss slowly in the next coming classes. So 3, we have also included another one. The combination of these two is giving you a fourth symmetry element, which is a combination of axis and plane. What plane is it? That we particularly define when we go to the improper axis, because whenever we say plane, it could be a vertical plane, it could be a horizontal plane, or it could be a dihedral plane. So with respect to the axis that we choose, what kind of plane are we choosing is very important. For this particular alternating axis of symmetry, whichever plane that we choose should be perpendicular to the axis that we choose. Suppose if I am choosing z axis, I am trying to rotate the molecule along the z axis imaginatively, then the plane that I have to choose is perpendicular to it, which is a xy plane. Or suppose if I am rotating the molecule along x axis, then the plane that I have to choose is yz. Or if I am trying to rotate the molecule along y axis, then the plane that I have to choose is xz, that is perpendicular to it. So always axis and plane must be perpendicular to one another. Only such a plane has to be chosen. Okay, that is a detailed explanation which we will discuss later, but that combination is giving you one more symmetry element. Apart from this, we also have one other symmetry element which has a least importance symmetry wise, but group theory wise it is having a greater importance, because for mathematical completeness of this symmetry, whatever molecule that you choose, for the mathematical completeness, that particular element is very much required, and that particular element is defined by identity. It is called as identity element, or it is indicated by a capital E or a uppercase E, which is referred as Einheit. Okay. What is this identity element? So, simplest of the examples is, well, my name is Dr. Shashikant, and suppose if I am in Hyderabad, I have my identity with my name, right? If I go to some college, then you call me as Dr. Shashikant, or simply you call me as a Shashi, right? I go to some other university, say in Delhi. Even when I go to Delhi, I don't lose my identity, I don't lose my name is still intact, right? That is giving me my identity. So, even at Delhi University I will be called as Shashikant, or if I go to Kerala or some other Tamil Nadu, wherever I go, I have my own identity, right? I don't lose my identity if I change my space. Just in a similar way, whatever molecule that we choose, now let me choose a water molecule, molecular model for H2O, or it could be H2S, or I am just say choosing CCl4, right? This molecule or this molecule has its own identity. That identity is not lost just by operating some symmetry element. I just ask you to pass a plane. Now, once you are passing a plane, all that is imaginary. So, once you are passing a plane, it is not bisecting the molecule practically, it is all imaginative. So, by putting some symmetry elements, it is not changing the molecule practically, all these are purely imaginary. So, whether you rotate this or not, it has its own identity. Whether you reflect or not, it has its own identity. Whether you invert or not, it has its own identity. So, every molecule has its own identity, and that is giving its another element called as identity element. Okay? So, that becomes the fifth element. Now, coming to the conclusion, what is a symmetry element means? It is an equipment with a chemist, so that I can understand what is the symmetry, or I can measure the symmetry that is present in a given chemical entity. There are three basic symmetry elements, one is axis, another is a plane, and third one is a point. The combination of these two symmetry elements called as axis and a plane, where one should be perpendicular or orthogonal to the another one, that will generate another symmetry element. And above all, every chemical entity has its own identity, whether you operate or not, rotate, reflect or invert or not, it has its own identity, and that identity is being preserved as an element called as identity element. So, when you consider these accessories called as a alternating axis of symmetry and identity element, now altogether we have 5 symmetry elements. Okay? From basic 3, now we are able to generate altogether 5 symmetry elements. Now, with these 5 symmetry elements, we can also have some operations. What are these operations? These are accessories, as I said, for our symmetry, but mathematically identity is very, very important. You just cannot neglect identity element. When it comes to the symmetry operations, how many symmetry operations are present means it is again 3. So, number 3 has a great importance. There are many examples that I even give in the regular classes. 3 number has a greater importance. Here the basic symmetry elements are 3. When we come to the symmetry operations, these are also 3. What are these 3 basic symmetry operations? We will see. With the help of an element, it is just like if I give you scissors, you try to cut. So, just in a similar way, if axis is taken, the symmetry operation that is performed around this axis is rotation. So, rotation is an operation which is carried out around the axis that is given. Axis is your element, rotation is the operation. Now, if a plane is given, what is the operation that we perform is reflection. So whenever a plane is imagined or whenever a plane is given, whenever I say it is given in our imaginations, okay. Rotation, reflection, and this reflection is an operation performed by taking a plane and with the help of a point, by taking the symmetry element called as a point, we can perform an operation called as inversion. We can just invert them. Suppose let me give a molecular model for ethylene. Now we have to choose some point. With this particular point, all the opposite identical points can be inverted, right? So that is called as an inversion. It is a separate element which we have to discuss. But inversion is an operation, rotation is an operation, reflection is an operation, inversion is an operation. We have three basic symmetry elements: axis, plane, and a point. These three basic symmetry elements can generate three symmetry operations: rotation around an axis, reflection along a plane, and inversion through a point. Combination will give you another symmetry element. And finally they have its own identity, that is providing you the identity element, okay. So this is a little basic about the symmetry elements present and the symmetry operations that are being generated by using these symmetry elements. Any proton or neutron is made up of 3 quarks, as I say. So again it is the number 3, or the basic subatomic particles, you say proton, neutron and electron, these are also 3. Now just with the help of a molecular model, I am trying to show the 3 spatial coordinates. The white ones are considered to be plus, green ones you can just consider to be them as minus. You just try to imagine plus x minus x, plus y minus y, plus z and minus z. This is with respect to a static point in the center. So you have to imagine a static point, and with respect to that point, just you have to consider these to be some coordinates: z coordinate, x coordinate and y coordinate, okay. Now getting to the next point, I will give you some basics that are related to these coordinates. Suppose if I ask you to rotate for any given molecule, I ask you to do some operation called as rotation, or if I ask you to do an operation called as reflection, what are the basic planes that are present which take up some coordinates? Or if I say some axis, first where you have to imagine this axis, this is at a basic level. Now once you are aware of all these basics, then you can just pass the rotational axis from anywhere within the molecule. But in the beginning stages, first of all you have to understand these coordinates. So when I say that try to pass a rotational axis, now we have to imagine a molecule. In that particular molecule, suppose if I am holding a molecule this way, I am holding the molecule this way. Now this become the z, this become the x coordinate, and this become the y coordinate. These are the coordinates. And whenever we say to operate that particular molecule, first thing that you have to do is to identify the center of gravity of this molecule. Once you identify the center of gravity, then that center point should become the center point of your coordinates, okay. Now these coordinates will vanish, all that become imagination. So now this becomes plus z, minus z, plus x, minus x, plus y and minus y. So when I ask you to operate rotation, then you try to pass an axis along z, you try to rotate. Or you may try to pass along y, you try to rotate. You may pass along x, you try to rotate. Some could be in plane rotations, some could be out of plane rotations, okay. As you are performing these operations, you have to check whether the given molecule is symmetric or not. All this is present in some patterns. So whether that particular pattern is repeating itself or not, by passing some symmetry element, we have to check. So we have to check this by performing some symmetry elements. As I said, I can pass an axis, rotate, or I may pass a plane, reflect, or with the particular point called as the center of gravity, you can try to invert them. Then you have to check the patterns present in the given molecule. Okay. So this is some basics of symmetry. Now in the next class, what we will discuss is how many different coordinates are there. Suppose if we take a rotation and if I ask you to rotate along z axis, which coordinate is exchanging and which coordinate do not exchange with the opposite coordinate. What I mean by saying this is, suppose if I ask you to rotate along z, will the z exchange into minus z or x exchange into minus x, y exchange into minus y or not, we have to see. Also another thing, if I ask you to pass a plane which is passing through some coordinates, which coordinates are exchanging with their opposite coordinates and which is not exchanging, we have to see. Once you are able to understand this, then symmetry becomes much easy, because in recent times in CSIR or GATE, even such basic questions are being asked. They will give you one particular operation. They may say that if at all you are trying to rotate along z axis, n could be some angle, which we will discuss in the next classes. Suppose if Cn is along z, you are trying to rotate and then you are passing a plane. How are the coordinates oriented? So such basic questions are also asked, and to understand all such basic questions, we will start with the next class. So let us continue with the various rotations and the symmetry elements or operations. Okay. So we were discussing about the various coordinates. First of all, I will give the conventions. This is pointing towards you, and whichever is pointing towards you is taken as x, opposite will be minus x. Every time we need not draw the complete coordinates, the opposite ones. If this is considered to be x towards you, minus x will be away from you, y towards your right, minus y will be towards your left, and z above and below will be minus z. So what we try to do is, let us start with the symmetry elements. In the previous class, what we said is we have three basic symmetry elements, but the combination of two other symmetry elements is giving you the fourth element, and the fifth element was identity element. Now for the discussion of the symmetry of a particular chemical entity, we have to go by these five elements. Though the basic are three, but they are also generating a fourth element along with the fifth identity element. So finally we have to consider the five symmetry elements, and each of these symmetry element, if we are trying to operate within the coordinates, how do these coordinates shift or do the coordinates exchange, that we have to discuss. When I say coordinate shifting or coordinate exchanging, suppose when I say coordinate is shifting, if it is moving from its position, whether it is moving from its position or not, we have to check. Or if I am performing such an operation where a plus coordinate could exchange with a minus coordinate, x coordinate could exchange with a minus coordinate, minus x, and plus z coordinate can exchange with a minus z coordinate. If we do such operations, and we will just try to find out which symmetry elements upon doing particular operations are changing the coordinates or the coordinates are not getting exchanged, we have to see. The five symmetry elements we said, the first one is an axis, second is a plane, third is a point, fourth one is a combination of axis and a plane, and the fifth one is an identity element. So depending on the particular symmetry element and the intricately related symmetry operation, we are trying to give the names of these elements. It is not just axis we say, but even along with the operation, considering everything, we give the final name. The first name is called as rotational axis of symmetry. We just need not write the axis of symmetry, I am simply writing rotational axis or proper axis of symmetry. So whether you say rotational axis or proper axis of symmetry. Now this particular symmetry element is simply denoted by Cn. All these are some symbolisms. It is called as a Schoenflies notation, which we'll learn, but this notation is called as a Schoenflies notation, where the rotational axis is defined by a capital C or an uppercase C with a small n or a lowercase n as a subscript. You have to put it as a subscript. Usually we put it, I mean some students put it this way. It is not the correct convention. What you have to do is, it should be a lowercase and it should be a subscript. So this is how we have to define rotational axis, a simple notation, and it is called as a Schoenflies notation. Second one is the plane of symmetry. Or reflection symmetry. Plane of symmetry or reflection symmetry, it is indicated by sigma. Third one, directly instead of taking inversion, what we do is we will take the combination of these two. The combination of rotation as well as the reflection perpendicular to it is generating another symmetry element. We call it as improper axis of symmetry, that is one name, or alternating axis of symmetry, where the rotation is alternated by reflection which is perpendicular to it, or the other name given is rotation reflection symmetry or reflection rotation symmetry. All these are different names given for this particular symmetry element. You may call it as an improper axis, alternating axis, rotation reflection symmetry, or a reflection rotation symmetry. This is given by Sn, uppercase S, lowercase n, it should be a subscript. Fourth one is an inversion center. You may denote it by I. And the last one is identity element. It is defined by E. So these are the 5 symmetry elements, and for our description how the coordinates exchange, whether they are exchanging or not, whether they are shifting or not, to understand we will try to apply these particular symmetry elements and then we will check it. So every time we need not write the complete name, I will take the notation Cn for proper axis, sigma for plane, Sn for alternating axis, I for inversion, and E for identity element. Okay, these things you have to remember. Now let me start with Cn. What is Cn means? It is a rotational axis of symmetry, and this rotation by convention you can take, or you can rotate along z coordinate, you can rotate along y coordinate, or you can rotate the molecule along x coordinate. So whenever we define Cn in brackets, if you put z, that simply means you are trying to rotate the molecule along z axis. The given axis is z. How much is n? It will be defined depending on the symmetry of that particular molecule. It could be 1, it could be 2, or it could be any different number depending upon the repeatedness that is present in the given molecule. Okay. Let us start with Cn along z. So whenever I am performing Cn along z, This is a convention, general convention that you have to remember. For the coordinates, for showing the coordinates, I am just erasing it. What we are trying to do is, we are trying to perform a rotation along z. So how much is n? Just let me take an example. Let me take C2 along z. What is C2, what is C3, we'll just come to know once we try to take up the rotational axis of symmetry separately. But for time being, C2 means 180 degree rotation. If at all I am trying to rotate through 180 degrees, what we get is a C2 rotational axis. That 180 degree rotation is through z axis. So now this is my imaginary axis. It is passing through z. And to what angle am I rotating it? The rotation angle is 180 degree. Only if I rotate by 180 degree, I get a C2. So just let me write it as a C2. Now just look carefully about the coordinates. That particular rotational axis is passing through z. And as we are rotating the coordinates along 180 degree, you can very carefully see that if this is plus y and this is a minus y, now 180 degree rotation will exchange plus y with minus y. Okay? X will be exchanged into minus x. So in a better view, I will show here. Suppose I am holding it this way. Now Cn along z axis. So this is the z axis, conventional, x and y. Along z axis, if at all I am trying to pass a rotational axis, we are trying to rotate by 180 degree. If this is my reference, right? If this is my reference, if I have started to rotate, now this is a 90 degree rotation. 180 degree rotation, 270, 360. Okay, I am just repeating it: 90 degree rotation, 180, 270 and 360. What is our example that we have chosen? It is a C2. C2 means it is a 180 degree rotation. So once I say 180 degree, now this I rotate to 180 will come here. As it is coming here, you can see that plus is exchanging with a minus. It simply means whatever entity that is present in the plus coordinate is now shifting into a minus coordinate. It is not that the coordinates are exchanging, plus and minus are exchanging. It is the position of that particular chemical atom which is being exchanged. From a positive coordinate, it is entering into a negative coordinate. Okay. Now you can watch. Suppose that there is an atom which is present. As I am rotating it, from a positive coordinate, it has entered into a negative coordinate. So only for our understanding, what we say is x coordinate is exchanging with minus x, for our understanding. Okay. Also you watch, this is okay, this is x and this is y, right? We just exchange it. Just imagine that this is x minus x, y minus y. Okay, just a small correction. Now this x is exchanging with minus x and this y is exchanging with minus y as I rotate by 180 degree. But one important thing that you are noticing is this rotational axis is passing through z, and as it is passing through z, plus z is not coming into minus z. Plus is in the plus and minus is in the minus coordinate. Okay. Whereas plus x is getting into minus x, plus y is coming into minus y. So this is the most important point which is to be noticed whenever we are performing some operation. So any rotational axis which is passing from one particular coordinate, that coordinate will not exchange, whereas the other coordinates will exchange with their opposite phases. This is the point. I am just repeating. whatever coordinate that you choose, from that particular coordinate, if at all you are passing some rotational axis, then that particular coordinate will not exchange with the opposite phase, whereas the other coordinates through which the rotational axis is not passing, they will exchange their phases. Plus will exchange with minus, plus will exchange with minus. But here plus will not exchange with minus. So this is the conclusive point. Okay, right? So the easiest way to remember is, from whichever coordinate rotational axis pass will not exchange its phase, but the other coordinates will exchange their phases. Now based on this, we can just see here it is passing through Z. So Z will not exchange with minus Z, Z will remain, but what happen is X will shift into minus and Y will shift into minus coordinate or the minus phase. In the beginning it may take some time for you to understand, but as you repeat your understanding, it will become easy for you. So Z is in the Z coordinate only, it is not exchanging. X is getting into a opposite phase. So now this becomes X. And Y is also coming into its opposite phase. So this is how the coordinates look like. Z remain there, Y is getting into minus Y, X is getting into the opposite phase minus, so we are writing it as a minus X. This is a C2 along Z operation. Z coordinate is remaining, whereas Y coordinate and X coordinate are exchanging with the opposite phases. Now let me do the same operation along Y and also along X. Then we will try to conclude it. Try to pass C2 along Y coordinate. We are trying to pass it along Y coordinate, and as we rotate, you can check here. Now the rotational axis is along Y. This is how we are rotating. In the previous case, this was the rotation along Z. So as we rotate, you can see plus Z minus Z, they do not shift their phases, whereas X and Y, they are shifting their phases. Now what we are doing is, instead of Z, now we are trying to pass it from Y. Okay. So as we are passing it from Y, this axis is passing through Y coordinate. Y will not exchange with its opposite phase, whereas Z will exchange and X will exchange. You can see. Now this white will exchange into this green, white will exchange into this green. Can you see? So exactly 180-degree rotation. Previously white was towards you. Now as I rotate by 180, that is being exchanged by green. In a similar way, previously white was here, that is exchanged by green. It means Z is exchanging its phase, X is also exchanging its phase, but Y is intact. Y is not exchanging with its opposite phase because that particular rotational axis is passing through this coordinate. So again we can make a conclusion, from whichever coordinate the rotational axis pass from, that coordinate do not exchange with its opposite phase, whereas the remaining coordinates will exchange. So first Y is intact, so let us keep Y intact. Y is not exchanging with its opposite phase. X is moving away into its opposite phase and Z is also moving into opposite phase. This is the reference point. Okay, this is about C2 rotation along Y. We have completed Z, we have completed Y. Now we have to go through X. Now this is the X. From your point of view, this is X. So if at all you are trying to pass a rotational axis through X, I am holding it here. Now you can see this is plus X, this is minus X. Plus will not exchange with minus, you can see. But what you find is, suppose if I am holding it this way, plus Z will exchange with minus Z, plus Y will exchange with minus Y. You can check it. If this is white, will be exchanged by green. If this is white, will be exchanged by green. It is a 180-degree rotation. But plus X is not being exchanged by minus X. So again the conclusion point, from whichever coordinate your rotational axis passing from, that particular coordinate will not exchange its phase, whereas the other coordinates will shift or it will exchange. When I say it exchange, it is 180-degree rotation. When I say it is shifting, these particular phases are shifting, it could be some other angle of rotation. So let us come to the third example. It is a C2 along X direction. We are rotating along the X coordinate. Now what happens is, from that particular point, X will be intact, X will not shift, whereas Y and Z has to shift. So it is a 180-degree rotation. This will be Z and this will be Y. But X is intact, this has exchanged, this has exchanged. Okay. Now what is the conclusion? You can just find out from the Cn, where I have taken an example of C2 along Z or along Y or along X. The final conclusion is, from whichever coordinate the rotational axis pass from, that coordinate will not exchange with its opposite phase, whereas the other coordinates will exchange with its opposite phases. Okay, or they will shift from their position. These coordinates will shift from their position, whereas the coordinate through which the rotational axis has passed, it will not shift from its position. This is the final conclusive point. And all these points where I repeat, you can just make a note of it in your regular book. Whatever I am drawing, you can just take it in a book. So the conclusion of all these diagrams where the coordinates are being shifted or exchanged, I will give it in the form of a table. Right, this is a table for C2. Now the symmetry element that we have chosen is a C2. The first one is C2 along Z, C2 along Y, and a C2 along X. These are the coordinate that is unshifted, coordinate or the coordinates which are shifted. So which coordinate will be unshifted? You just remember this. Whenever in the exam they give you C2 along Z, it means C2 is passing through Z. Z will not be exchanged. So the unshifted one is Z. C2 along Y, Y will be unshifted. C2 along X, X will be unshifted. Whatever remaining coordinates that are present, you just write it. This is C2 along Z, X and Y will be shifted. If it is a C2, they exactly exchange with their opposite phases. X will get into minus X, Y will get into minus Y. If it is a C2 along Y, Y is already here, so you just put X and Z. If it is a C2 along X, X is already here which is unshifted, so the shifted coordinates will be Y and Z. So it is that easy, but that conclusive point is most important. From whichever coordinate the rotational axis is passing from, that coordinate will not exchange with its opposite phase, whereas the remaining coordinates will shift. If it is a C2 rotation, they exactly exchange with their opposite phase. Okay. So this is a table for a C2 rotation along X, Y or Z axis. If it is a singular one, we call it as axis. If it is plural, we call it as axis. That is the difference. Now this is for rotational axis, which is the first symmetry element. We have also seen different symmetry elements. The second one was a plane, or you call it as a sigma symmetry or a plane. Even for that plane, how all these coordinates will shift or how do those coordinates exchange, we will try to see. You can pass plane from any coordinates that you like, or you can pass it in between the coordinates. But as a beginner, what we generally imagine is, whenever I say pass a plane, usually to define all these orbitals or for our symmetry considerations for chemical entities, we consider 3 different planes. Okay, you can also choose a plane that is present between the axes. But whenever the axes are given or the coordinates are given, how many planes can you generate means, at the most we can generate only 3 different planes by choosing the 3 coordinates. So what are these 3 planes? Let me provide you. Supposing that I am choosing the 3 planes. First let me write the coordinates. Now if I am trying to pass a plane, which is taking up X and Z, this become one plane XZ. Okay, or I may choose another plane which is taking up Y and Z, this become YZ plane, and the third one is a XY plane. So each plane is taking up 2 coordinates. Therefore altogether we get only 3 planes when I consider the coordinates. If the plane is between the coordinates, you can generate n number of planes, but through the coordinates at the most we can generate 3 different planes. So what are these 3 planes means? One is a XY, XZ and YZ. A plane is represented by a sigma, so simply you can put it as a sigma XY, sigma XZ and sigma YZ. So which coordinates exchange when I pass a plane and which coordinates do not exchange, we will try to figure it out. Let us start with the first one, sigma XY. How to denote sigma XY? First let us learn. Now this is X, Y and Z. So simply draw 3 lines or the 3 arrows. Then you put X, Y and Z in an anti-clockwise manner. That is a general convention. Or you can just hold the hand, you can just put the hand in this way, open the fingers, first, second and third. Now this will become X, Y and Z, just like in an anti-clockwise manner. It is a XY plane. It means that plane should take X and Y coordinates. So this is how the plane is. This is a sigma xy plane. Now what you find is it is passing through x and y. So this y will remain here itself, it will not exchange with its opposite face. X will remain here itself, it cannot exchange with its opposite face. But as it is passing through x and y, z is above and that z will reflect below. What is this reflection? What are these operations? That has to be discussed separately, but from your basic knowledge you are aware of, as I pass a plane, it will have a reflection. The operation that we carry out is a reflection that will be reflected in exactly the opposite direction. Okay. So I am saying that it is a sigma xy. Since that particular plane is passing through x and y coordinates, x and y coordinates will remain in their position. They do not exchange. But when it comes to the z, it will exchange with its opposite face. Okay. So whichever coordinate is perpendicular to your plane, only that coordinate will exchange with its opposite face. Those coordinates which are within the plane will not exchange with their opposite phases. That is the important point that you have to remember. So once I perform this, what is the resultant? We have a point. From this particular point, since that plane is passing through x and y, these x and y do not shift, but z will undergo a shift. Okay, this is the resultant of this particular sigma xy plane. So now I think you might be getting some conclusions. From whichever coordinates the plane pass from, those coordinates do not shift or those coordinates do not exchange, but the other coordinate which is perpendicular to this will shift. Sigma xy is completed, then we will take sigma xz from a point now xz is this plane. Okay. It is this plane xz. It is passing through x, it is passing through z. So these coordinates do not shift. But y, it is just perpendicular to this plane, so this y will reflect in its opposite face. This is the resultant. And the last one is a sigma xz yz. YZ is a plane which is the plane of your board, or if at all you are drawing it on a paper, it is a plane of your paper. Now since this particular plane is passing through y and z, those y and z will not shift, whereas x will be reflected in its opposite face. Okay, so since it is reflecting in the opposite face, you put minus. For that reason I have put a dotted line. So this is the conclusion. I am repeating the final point for the plane of symmetry or the sigma symmetry. From whichever coordinates the plane pass from, those coordinates do not shift their position. They do not shift with their opposite phases. But that coordinate through which the plane is not passing from, or that coordinate which is perpendicular to the plane, will undergo a shift. That will exchange with its opposite face. In the first case, it is z. In the second case, it is y. and in the third case it is x. So just by looking at the three planes, the logical point you might have got it. What is that logical point? Just by looking at the plane you can say which coordinate is exchanging. It is an xy plane, z is absent, so z will exchange. Xz plane, y is absent, therefore y is exchanging. YZ plane, x is absent, therefore x is exchanging. That is how we try to remember. In the case of rotational axis, previously what we have seen, from whichever coordinate it is passing from, that will remain there. Suppose if I put C2 along z, which other coordinates are shifting means whichever is not present here, they will shift. X and y will shift for rotation. But for reflection, whichever are present here will stay intact, whichever is absent will exchange. So it is just the reversal of rotation. Now from these three diagrams, again we will try to construct a table. These tables will be very, very useful for you during the time of examinations. Right, now here we have a symmetry element, which are the coordinate or the coordinates that are shifting and which are the coordinates that are unshifted. We are taking planes sigma xy, sigma xz and sigma yz. So which coordinates are being shifted? xy do not shift, z will shift. This is a xz plane, whatever is absent here will shift. Yz plane, whatever is absent here will shift. And when it comes to the coordinates which are unshifted, you can just watch here. It is a plane which is passing through xy, so just make x and y are unshifted. It is a sigma which is xz, so x and z will be unshifted. And this is a sigma which is passing through yz, therefore y and z will be unshifted. So for the rotation I have given you a table. This is for a reflection. The easiest way to remember is whatever plane that is given to you, in that particular plane whichever coordinates that are present will not shift their position, whichever coordinate is absent that will shift its position. You can just say it from sigma xy, xz and yz. Okay? This is a point which we have taken in the previous table. Now C2 which is passing through z, z will not exchange, y will not exchange, x will not exchange, whereas the other coordinates will exchange. Plane is little bit reverse to that of the rotation. So these are the two important tables which you have to remember. We have seen some basic questions. As I told you in the CSIR and GATE exams, they will give you a combination of these operations. They will ask you when Cn is performed followed by a particular plane, how are the coordinates shifted? What is the final position of these coordinates? You have to remember on these two tables that I have given you. Now that is with respect to the basic symmetry elements, rotation and reflection. Let us take the third symmetry element, which is Sn. As I told you, it is a combination element. Sn is a combination of Cn and a plane which is perpendicular to the CN. So whenever I say a plane which is perpendicular to the CN, you call it as a horizontal plane. You call it as a sigma h. So it is a CN and a sigma h. Sn is called as a combination element. Just in a similar way what we have done previously, we will also try to do here. Let me take S2 along z axis. When I say S2 along z axis, it will be C2 along z, and it is a sigma which is perpendicular to this. It is a sigma h. So whenever I am choosing a rotational axis passing through z, the plane present perpendicular to it will be sigma xy. In the previous plane we have seen, for z axis perpendicular plane will be xy. If the axis is z, its perpendicular plane or a horizontal plane will be xy. If the axis is y, it will be xz, and if the axis is x, the perpendicular plane will be yz. So on that basis, here what we are doing is S2 is being performed along z axis. It simply means C2 along z followed by a plane perpendicular to the z axis, which is a sigma xy. Let's begin with the 3 coordinates. So the first operation we are performing is C2 along z. Now as we can see, when we perform C2 along z, x will exchange into minus, y will exchange into minus phase. Okay. Now this particular rotation is followed by a plane perpendicular to this rotation. So I will show in one particular diagram. For each and everything we need not draw. If one you can able to understand, this is by performing C2 along z. When I perform C2 along z, z will be intact. This is y. And this is x. This is only half an operation. Sn, as I said, it is a combination operation. Cn performed a Cn followed by perpendicular sigma. Now this is a sigma xy. Right? Xy has to be passed. So where is this xy? This is the plane which is perpendicular to the z. Okay. So once I pass this xy, you can see minus x is intact. It cannot reflect here. It is within the plane, so it will not exchange. Y is within the plane, it will not exchange. But z is above the plane. Now if this is the plane, z will reflect below. So what finally happen is, from the center point, x and y are intact. Now z is being reflected into minus z, minus y, minus x. So what conclusion do we find is, whenever I am performing an Sn operation, one of the examples that I am choosing is S2 along z. When I say S2 along z, it is a C2 along z followed by a plane perpendicular to it. The plane perpendicular to the z axis is xy. So the final operation is a C2 along z followed by a sigma along xy. I have taken the 3 coordinates. Then I have started to perform C2 along z. As I perform C2 along z, that particular coordinate will not exchange, whereas the other 2 coordinates will exchange, or they will shift into the opposite phases. So x is entering into minus x, y is entering into minus y, z is intact. This is only half an operation. This must be followed by another operation, which is a plane passing perpendicular to the z, because this is our conventional rotational axis, C2 along z. Now as I pass a plane, whichever is present above the plane will reflect below the plane, and whichever is present within the plane will stay there itself. Within it there is a reflection. That is a little bit a difficult point, we will discuss it later, but suppose if this is y and I am passing a plane through y, within itself it will exchange, but it will not exchange with its opposite coordinate. That is the difference. Exchanging with its opposite coordinate will be done by a coordinate which is perpendicular to that plane. But if any coordinate is present within the plane, then within that coordinate there will be an exchange, but this will not exchange with its opposite face. Okay, we will come to it later, but this is a C2 along z, x and y have exchanged. Now I am performing sigma xy. As I perform sigma xy, z is also reflecting. So what is the final conclusion? X is getting into minus x, y is getting into minus y, and z is getting into minus z. It means whenever I perform an SN operation, all the three coordinates are being exchanged. This is just one example that I am giving you. If you try to perform S2 along y, right, or you may also perform S2 along x. I am not doing all these things, I am just saying that S2 along y, it is a C2 along y, sigma along xz. Whichever coordinate is present here, do not repeat it here, that becomes a sigma h for this. And S2 along x, it is a C2 along x and sigma along yz. So as you perform C2 along y, x and z will exchange. As you perform sigma xz, y will also exchange. So all the three coordinates will exchange. Even when you come to S2 along x, C2 is along x, y and z will exchange, and as you pass sigma along yz, x will also exchange. So if at all you perform S2 along x, or whether you perform along y, or whether you perform along z, all the three coordinates will undergo a shift. One representation I have shown it here. Now the conclusion of S2 along z, x or y, I will give it in the form of a table. So that will complete the conclusions for Cn, sigma and also Sn. For Sn, symmetry element, I am giving you the table. S2 along z or right. Now which coordinates will shift? It is a combination operation. Let us start with a C2 along z, then followed by a sigma along xy. C2 along z, that z will not shift, but which is shifting means x and y will shift, z will remain there. When I pass xy, z will shift. It is shifting into its opposite phases, minus x, minus y, minus z. We need not represent it. We are simply saying which coordinate is being shifted, those coordinates are being represented. Okay. So which is unshifted? Every coordinate will shift whenever you perform an SN operation. Then coming to S2 along Y, it is a C2 along Y. Since it is along Y, Y will remain intact, X and Z will exchange, but it is a sigma along XZ, so Y will also shift. All the three coordinates are being shifted, there is no coordinate which is unshifted. And finally S2 along X, it is a C2 along X, so Y and Z will shift, sigma along YZ, X will shift. There is no coordinate which is unshifted. So what is the conclusion? Whenever an SN operation is performed over any molecule that you choose, all the three coordinates do exchange. They will exchange with their opposite phases. There is no coordinate which is remaining unshifted. Okay. In rotation we have seen two coordinates are shifting. In plane we have seen one coordinate is shifting. In SN, which is a combination of both but a perpendicular plane, we are seeing that all the coordinates are being shifted. No coordinate is left unshifted. The next symmetry element is inversion, right? In this inversion, what we do is, suppose if I am choosing any molecule, or you can just imagine these to be the coordinates. From a center of point called as a center of gravity, all the opposite identical points, they get inverted. So if this is plus, this will exchange with minus, plus will exchange with minus, plus will exchange with minus. Okay. So this is how it will come. When plus will exchange with minus, okay, previously it was this way, and as they get inverted, this is how you will see it. Wherever you had white balls, now they are replaced by green balls. So this is process of inversion. All these symmetry elements will be discussed under these separate headings, but this is just a conclusive tables. In the beginning, once you are aware of which coordinate is shifting, which coordinate is unshifted, that will be a very strong base for your symmetry considerations. So let me start with inversion. I don't say that inversion is along X or along Y or along Z, because inversion is carried out through a point. So once I say it is through a point, through that point X, Y and Z are generated. So you never say I along Z, I along Y, I along X. It is simply I. It is inversion because it is from that point which is generating all these coordinates. So once it is a point, you need not define it by any coordinate. This is that particular point, and with respect to this point, X will exchange with minus X, Y will exchange with minus Y, Z will exchange with minus Z. So that inversion is carried out through a point called as center of gravity. You don't put IZ, IX or IY. What is happening? Now from that center point, Z is getting inverted, X is getting inverted, and even Y is getting inverted. So this becomes minus Y, minus X and minus Z. Coming to the conclusive table, coordinates or the coordinate shifted and unshifted ones. Element is inversion. which coordinates are shifted means x is being shifted, y and even z, all the three coordinates are shifted. There is no coordinate which is unshifted. So if we just carefully look at the conclusions for inversion, you try to compare it with the Sn. Even in Sn, which is a combination element, that could be along Sn along z, or it could be along y, or it could be along x. So whatever result that you are getting by performing S2, I am particularly speaking about S2, okay, because in S2 only it is a 180 degree rotation followed by a perpendicular reflection. So for S2 along z or S2 along y or S2 along x, whatever result that you got, the same result you are also getting by performing an inversion. So for this reason, in symmetry we say that S2 is equivalent to inversion. That S2 could be along z, y or x. Simply S2 is equivalent to inversion. Whatever result that you get by performing S2, the same result you will also get by performing inversion. Okay. This is about inversion. Then the last one that we have is identity. What is identity? Identity is defined by or indicated by E. It is a unity. We will arrive it in the group theory. What is an identity operation? This is an element, and what is the operation that we are performing? For axis, the operation that we have performed is rotation. For a plane, the operation we have performed is reflection. For a point, the operation we have performed is inverting or inversion. For Sn, the operations are rotating followed by a perpendicular reflection, and for identity element the operation is nothing, or you simply call it as a doing nothing operation. What is identity element means? It is a doing nothing operation. It is a doing nothing operation. Or suppose if I am holding a water molecule, you just do nothing on this, let it be there. You don't try to rotate imaginatively, you don't try to rotate, you don't try to reflect, you don't try to invert. Still it will retain its own identity. So once you are doing nothing, it has its own identity. All the coordinates also stay intact. They do not exchange with their opposite phases. Z will remain, Y will remain, and also X will remain in its position. They will not exchange with their opposite phases. Got it? So it is called as a doing nothing operation. Or if at all you try to perform any operation, it has to be a complete operation. What do I mean by a complete operation? If you are trying to rotate a given molecule from a particular coordinate, you have to rotate by a 360 degree angle. Then it is called as a complete operation with respect to rotation. Suppose if it is a reflection, try to perform even number of reflections. Suppose if it is an inversion, try to perform even number of inversions. Then it is called as a complete operation. So if at all you are doing nothing, you can generate identity element, or by doing a complete operation you can generate identity element. But in either way, all the coordinates will be intact. The coordinates will not exchange. So don't go for symmetry operations, reflecting, all those things. It will be little bit difficult. The final result will be the same. So instead you do nothing. So once you do nothing, what will be the result of this? When you do nothing, all the coordinates will stay at their positions. So X will remain, Y will remain, and also Z will remain in their positions. Now if at all we try to conclude in the table, identity, okay, which coordinates are shifted? No coordinate is being shifted, but which are unshifted? All the coordinates are unshifted. So this is just like a reverse of the inversion. Inversion is just similar to that of the S2 along Z. And C2 and sigma, the coordinates that are exchanging, they also look little bit reversal to one another, right? So these are the conclusions of all the symmetry operations performed over the symmetry elements, by taking these symmetry elements, and we are performing this on the coordinates. What coordinates did we choose? X, Y and Z. So once you are performing all the symmetry operations by taking the symmetry elements on the particular coordinates, how are these coordinates shifted or unshifted? We have seen in the form of a table. Once you are able to understand all the symmetry operations, how the coordinates are shifting, that will be very, very useful for you to understand the symmetry of each and every molecule. So the next topic will be, we'll take up individual symmetry elements, and by taking each symmetry element, we'll try to see how the operation provides you a different configuration. Okay. With this, we'll stop this class. After the basics of the coordinates that we have seen, how the coordinates exchange or shift whenever we operate a particular symmetry element, we have taken the conclusions. Now let us come to each and every symmetry element. Okay, the 5 symmetry elements that we have discussed in our last classes. Today, in this class, we will begin with symmetry elements. The first one being rotational axis of symmetry. We also call it as proper axis. It is denoted by Cn. C should be uppercase, N should be lowercase, and it should be a subscript. That is called as a Schoenflies notation. Schoenflies notation we will discuss when we take up the point groups. Now this rotational axis of symmetry, or we also call it as a proper axis of symmetry, where we use a symmetry element called as an axis, and the operation that we perform is a rotation operation. So whenever we say that we are performing a rotation operation, that particular rotation operation could be a clockwise rotation, or it could be a counterclockwise rotation. Counterclockwise we say anti-clock. So it could be a clockwise rotation, or it could be a counterclockwise rotation. But by convention, we mostly follow clockwise rotation. So whenever I indicate it this way, it is a rotation and it is a clockwise rotation. Right. Coming to the rotational axis of symmetry, or proper axis, we have indicated it by Cn, and what exactly is N? We refer it as fold. What does this fold mean? Imagine that I am taking a molecule and I have passed a rotational axis. Once I have passed a rotational axis, then I am rotating it to some point where I get a particular configuration which looks just similar to the original one, and I rotate some other I perform some other rotations where I finally arrive at the identical configuration. So whenever I rotate it to some angle, I am rotating it to 360, and as I am rotating by 360 degree, at some particular point you will get a configuration that looks just similar to that of the original one. So how many times such a pattern is being repeated is indicated by n, or n is simply called as fold. How many times the molecule is to be rotated to get original configuration. Okay, how many times a molecule is to be rotated to get into original configuration. What does it mean, how many times the molecule is to be rotated? Everyone will say that only by once I rotate it is getting into original configuration. Or okay. Just a second. ఒక్కసారి From the basics of the last classes, where we have discussed how the coordinates behave when we operate the symmetry elements, now we will try to arrive at various symmetry elements. We will discuss in detail about each and every symmetry element. So as we discussed in our last classes, we have 5 different symmetry elements, the first one being the rotational axis of symmetry. In this class we will start with the rotational axis of symmetry. We also refer it as the proper axis of symmetry. This is indicated by a Schoenfeld notation Cn, where C is the uppercase, N is the lowercase, and N should be subscript. In this Cn, we see an alphabet N. What does this N indicate? It will indicate fold. And what is this fold means? Whatever molecule that we choose, we rotate it certain number of times so that finally we arrive at an identical configuration. And how many times we have rotated, and while we rotate to 360 degree, how many times the molecule is repeating itself. Suppose if I am choosing a one particular configuration, and as I rotate, if you get another configuration which cannot be distinguished from the original one, you call it to be an equivalent configuration. So how many times the molecule is repeating itself, that is defined by the fold. It is the number of times the molecule is to be rotated to get identical configuration. That is represented by fold. We also call it as periodicity. We will explain it by taking some examples, but N is called as a fold or periodicity. N is given by 360 degree upon theta, where theta is the angle of rotation. So what is this theta means? It is that angle when we rotate the molecule, it comes into another orientation or configuration which looks exactly as that of the original configuration. For example, I choose a water molecule. For this water molecule, if I rotate by 180 degree, that will just look like the original one. So that particular configuration where I am rotating the molecule into 180 degree, that is called as an equivalent configuration. I rotate by another 180 degree, whatever configuration that will result, it will just look like the original one. So I have rotated completely 2 times so that I get the original configuration, which we call it by some other name. This terminology also I will introduce, but just for meanwhile, N equal to 360 degree upon theta. Theta is the angle of rotation. What is that angle? It is that angle when you rotate the molecule just looks like the original one. It is not the original configuration, but it just looks like the original one. So we call it as an indistinguishable configuration. And that angle for water molecule is 180 degree. So what is N for water molecule means? It is 360 degree by 180 degree. That gives you 2. So for this reason we say water molecule has got a C2 rotational axis. C2 rotational axis. 2 represents the fold. So which fold is the principal axis in water molecule, means it is a two-fold rotational axis. Whenever we have C2, we have to read it as two-fold rotational axis. Suppose if it is a C3, I choose some other molecule such as ammonia, then in that we have a C3 axis, we have to read it as a three-fold rotational axis. That is the difference. So you need not directly say C2, we can also say it as a C2, but we have to say two-fold rotational axis, or it could be a three-fold, four-fold, that depend on the molecule that we choose. What is this configuration terminology I will introduce? For rotational axis of symmetry, we have some different terminology, and whenever I say configuration, you need not confuse it with the stereochemical configuration in your organic chemistry. This configuration is just how the atoms are configured in a given molecule. First, let me start with the original configuration, or if you are confused with the terminology configuration, you can use the term orientation. These are the three different terminology that we have started to use. Original configuration is the configuration from where we have started the molecule. Suppose I have chosen a molecule, now I have started doing some operation on this molecule. So from whichever orientation or whichever configuration we have started from, that configuration is called as a original configuration. Now once I have taken a molecule, then I started to rotate it, and the conventional axis that I have chosen is along Z. Okay, you need not choose it along X or Y, because when you choose it along X or Y, you will not get any such rotations. You will only get a C1. But whenever I am passing it through the Z axis by holding the molecule in this manner, then we get a particular angle 180 degree. It is just looking similar to the original one. This is the original configuration. Okay, I am just repeating this. This is the original configuration. Imagine that this is H1 towards your right hand side, H2 is towards your left hand side. Now as you rotate, to what degree you have to rotate? If I rotate it maybe say 30 degree. So once you rotate it to some angle, then you have to check this orientation or the configuration with that of the original one. This was the original one. You have to compare these two configurations. Are they looking alike? You have to say. Now if this is the original configuration, this is 30 degree configuration, these two are not looking alike. So this 30 degree rotation operation is not valid. Maybe I rotate it by 60 degree. So original configuration, you have to keep it in your mind, right? This is your original configuration. Now I rotate it by 30 degree, compare it with the original one, it is not looking alike, leave it. Rotate it by 60, not looking alike. Rotate it by 90, not looking alike, because the first configuration was this way. I will just show you with now this is your original configuration that I am holding. Imagine that this is H1 towards the right hand side, H2 is towards your left hand side. With respect to this original configuration, now we try to rotate. This is your conventional rotational axis along Z. I rotate it by 30, 50, 60, 70 or even 90, it is not just looking like the original one. This is 90 degree rotation. H1, you just see H1 is moving from your right hand side, it is slowly moving towards you. Now I still rotate, now I have rotated it to 180 degree. This is a 180 degree rotation. So once I have done a 180 degree rotation, H1 which was towards your right hand side has moved towards your left hand side. Now once when it is reached to 180 degree angle, it is just looking like the original one, right? It is just looking like the original one, but is it the original configuration? Absolutely not. It is not the original configuration. Original configuration is the one which I am holding in my left hand. This is another configuration which is just looking like the original configuration. Though it is just looking alike, but it is not the same. H1, which is towards your right hand side in the beginning, now it has moved towards your left hand side. But it is just like if you close your eyes and open, whether I rotate it or not, it is just indistinguishable from the original one. You cannot distinguish whether I have rotated it or not, because it is just looking like the original one. So that particular configuration which is just looking like the original one, but which is not, that is called as an equivalent configuration. This is just equivalent to this, but it is not the same. Such a configuration we refer it as an equivalent configuration. Okay. So when I rotate it by 180 degree, it is just equivalent. Then I rotate it by 200, 210, slowly I move 270, 300. It is still not looking like the original one. But when I do a 360 degree rotation, a complete rotation, now it is just looking like the original one. H1 again has come towards your right hand side. So from the original configuration where I started moving it at 180 degree. I got a configuration which is just looking like the original one, but which is not, because the hydrogens have shifted their position. So this particular position which is indistinguishable from the original one is called as an equivalent configuration. Then I further rotate it by another 180 degree. Now I got a configuration which is just looking like the original configuration. So whichever configuration is just looking like the original one, where the position of the hydrogens is also similar to the or the same as the original one, H1 is again towards your right hand side, H2 is towards your left hand side. This particular configuration which is same as that of the original one is called as identical configuration. Hope you got the point. So what is the relation between original configuration and equivalent configuration? Means they are similar. They are not the same, but they are similar. Original and equivalent, they are similar. Equivalent and identical, these are also similar. But identical and original, these are the same. They are just the same. If H1 is towards your right hand side, again in identical configuration H1 is towards your right hand side. So they are same. But in equivalent configuration, the position of the atoms may change, but it looks like the original one. It is this one. I am showing it again. This is original configuration. H1, imagine it is towards your right hand side, H2 is towards your left hand side. I am starting with it. I slowly started to rotate. To whatever degree that I am rotating, it is not just looking like the original one. It is not even equivalent to it. So as I rotate, I rotated it to 180 degree. Now it is just looking like the original one, but it is not the same. It is similar, but it is not the same, because the position of the hydrogen atoms is shifted. Then I again rotate it by another 180 degree. Now I got a configuration where the hydrogen 1 has come to the position of hydrogen 1. It is same as that of the original one. This particular configuration which is same as that of the original one, we are referring it as identical configuration. But whichever is similar to the original one, we are calling it as equivalent configuration. Okay. So how many times did I rotate? If I am choosing a water molecule, how many times did I rotate to get an original configuration? Once I rotated, I got equivalent, then I rotated, I got identical. So I have rotated 2 times. Then I got an identical configuration which is same as that of the original configuration. For that reason we say 180 degree and a 180 degree rotation. So we have rotated twice, and the fold is 2, C2. 360 degree, what is the angle of rotation? 180. We have rotated twice. So water molecule has a C2 rotational axis. That is how we have to conclude. You have to remember this terminology, and if at all you are confusing with configuration, you can just replace the term with orientation. But do not confuse this configuration with your stereochemical configuration. It has nothing to do with that stereochemical configuration. It is simply the bonds that are emerging out from the central atom. So don't go for R, S or D, L, etc. Okay, don't go for that. Now to give you a bit more understanding, let me take some circles. You may just call them as stereographs. You can just go on making large number of circles depending on the kind of rotational angle that we are making. Now from the first circle, what I do is, let me take a 0 degree angle starting from here. If this is 0 degree, then this will be 90, 180, 270. In between we have, if you want, you may indicate some other angles, 30, 60, and once I complete it, that becomes 360 degree. So starting from 0 degree, as you rotate, finally we are ending up at a 360 degree angle. Now in this stereograph, let me take a point at 0 degree. Let me just take a point at 0 degree. What we have to understand is, 0 degree, this point is at 0 degree. To what degree if I rotate, I get another stereograph which looks just like the original one. To what degree should I rotate the point to, so that it just looks like the original one? You can try. That point is here, okay. So once that point is rotated to some other angle, now let me say that it is about 30 degree. Here was a point. Now I try to rotate. I am trying to rotate that point to 30 degree. When I rotate it to 30 degree, whatever configuration that I got, is it looking similar to the original one? Answer is no, it is not looking similar to the original one. Neither it is same as that of the original one. So this is not an equivalent configuration, it is neither an identical configuration. So 30 degree rotation is not a valid operation. That is what we have to understand. 30 degree rotation is not a valid operation. Whenever I say that we have to rotate, then immediately you take some angle, you try to rotate and you say I got 10, 20, 30 rotations. It is not the exact answer. We require those rotations which are only valid. 30 degree rotation is invalid because it is not looking similar to the original one. Then I still rotate. I come to say 90 degree. So the point was at 0, now I rotated it to 90, now this is the point. These two, they are not identical, neither they are equivalent. I rotate it by 180, still it is not equivalent because the point is above. In this case the point has come below. So even if I rotate by 180, it is not equivalent, neither it is identical. 270 not equivalent, identical. But when that point comes to a 360 degree angle, when I am rotating it by 360 degree, now you can see this is just looking like the original one. So I have reached a configuration where it is just looking like the original one, and this is a 360 degree rotation. This is called as an identical configuration. So as I am rotating it, I did not get any equivalent configuration. You have to remember this point. In the previous circle I have given you original configuration, equivalent configuration and identical configuration. That is okay for most of the molecules, but there will be some molecules where you do not find any equivalent configuration. There is no other configuration which is equivalent to the original one. You have to directly arrive at identical configuration. We will take up some such molecules also. Okay, some asymmetric molecules will have only C1. It will not, they may have C2, but you call it as a dissymmetric molecules. That we will discuss in optical activity. But what is the conclusion is, as I rotate that particular point to any other angle, you are not getting any equivalent configuration. So I am rotating it by 360 degree. This is a stereograph for C1. Now let me take 2 points. These 2 points are exactly opposite to one another. The 2 points are exactly opposite to one another. So this is a 0 or a 360 degree angle. (90, 180 and 270). Let us start to rotate these 2 points in tandem simultaneously. So as I rotate these 2 points, now just imagine that the 2 points have come to 90 to 70 degree angle. It means I have rotated it to 90 degree. Once I have rotated it to 90 degree, whatever configuration that you are getting, it is not equivalent nor identical to the original configuration. So 90 degree rotation is not a valid rotation because it is not looking equivalent or identical. Then what I do is I still rotate the points beyond 90. I go to 120, I go to 150, now I come to 180. So when I come to 180, this is how they look. Once I rotate it to 180, this is how they look. If I don't mention these points, suppose if I give some identity to these points saying it is 1 or 2, if I give an identity, only then you will be able to say that 1 has moved into the position of 2, 2 has moved into the position of 1. If I don't label them, if I don't put any reference, it is absolutely difficult for any person to say that some rotation operation has been carried out. It is almost impossible to say. So this particular configuration, which is indistinguishable from the original one, is referred as an equivalent configuration. It is not an identical one. Why it is not identical? Because if this is 0.1, this is 0.2, upon 180 degree rotation, 0.1 has come to the position of 2 and 2 has come to the position of 1. These two, they are looking similar, but they are not the same. So for that reason, again I have to rotate by another 180 degree, then you will get a identical configuration which is just the same as the original one. Now to what angle did I rotate it? To 180. 1 was here, 2 was here. I rotated by 180. It is equivalent. Rotated by another 180, that will be identical. So I am doing 2 such rotations. So this will have a C2. Okay. Or in another way, to find out what is the fold, what we are doing is Cn, you don't know the n, then it is 360 degree by theta. How much is the theta? We are rotating by 180 degree. As you rotate by 180, you are getting a configuration that is indistinguishable from the original one. So you say the theta is the 180 degree. You cannot take 30, 90, 60, 65, whichever angle that is possible you cannot take. Only the valid symmetry rotational operation has to be taken. The valid one is a 180, take it here. 360 upon 180 will give you 2, so it is a C2 rotational axis. This is a C2. Suppose if I choose one point here, second point here, third point here. So where do they fall? Let me take it as a 0 degree and a 360 degree. This become 90, 120, 150, 180, 210, say 240, 270, 300, 330. You can also take 30 and 60, right. Now you can just look at the relation between the 3 points that I have chosen. These 2 points, they have a linear relation. This will be important when we go to the application part of the symmetry. These 3 points, they have a triangular relation and all the 3 points are identical. They are not different, they are identical. So for these 3 identical points, it has a triangular relation and the angle is also the same. So from 0 to 120, from 120 to 240 is again 120, from 240 to 360 is again 120. So these points are separated by an angle of 120, 120 and 120. It means it is an equilateral triangle. So whenever you get such 3 points, then what you have to do is, if this is your rotational axis, then start rotating it. In this case, I rotated it by 180, I got a equivalent configuration. In this case, when I start rotating it from 0, as I come to 120, if this is point 1, that point 1 has come into the position of point 2. From point 2, it was reaching into point 3, and 3 will reach point 1. All these things will take some examples, we have to separately work them out, but in this case you can just see 1 has taken the position of 2. So once it has come into the position of 2, whatever configuration that we are getting, it is equivalent configuration, because it is just looking similar to the original one, but it is not the same. So this is a stereograph for C3. Likewise, you can also take for C4. This will be 1 point, 2, 3, 4, and for C5 these are the points. So you can just make a 72-degree separation for that, and for this it is a 90-degree separation. And once you rotate, you will get equivalent configuration. How many times should I rotate? Means I have to rotate 4 times to get identical configuration. I have to rotate 5 times to get identical configuration. If I say take C6, you have to rotate 6 times to get identical configuration. Okay, so these are the stereographs for rotational axis. So what did we understand from this? Whatever point that we choose, that particular point, whenever we are rotating it, you may get an equivalent configuration, or there are some molecules where you don't get any equivalent configuration. You have to rotate it to 360 degree, directly you will get an identical configuration. So you will say that it is having only C1. But if the 2 points, they can exchange one another where they are indistinguishable but not the same, then you will get C2, or you may get C3, C4, and so on. Now we will take an example. We will choose an example. With respect to that example, we will say which one is the original configuration, identical or equivalent configuration. The basic of the examples is a water molecule. Right, I have chosen a water molecule. Then what I will do is, I will ask a simple question. Now I will try to pass a rotational axis from here. Then I will try to rotate. I am just passing a rotational axis from a bond between an oxygen and a hydrogen. Will it be a valid rotational operation? That is the question. Then the immediate answer would be, it is wrong. I just cannot take a rotational axis between the bond present between oxygen and hydrogen. It is not possible. So this is invalid. Or can I rotate it from here? Again it is invalid, because if you try to take a rotational axis from the bond, you will not get any equivalent configuration. You may get identical configuration, because whatever molecule that you choose, if you rotate by 360 degree angle, you will definitely get, you are bound to get a identical configuration when you rotate by 360 degree angle. But while you pass it from the bond, or if I try to pass it from the hydrogen, you try to rotate by some other angle, you will never get identical configuration. It is only, you will never get an equivalent configuration, not identical, you will never get a equivalent configuration. So what is the prerequisite? What is the prerequisite for passing the symmetry elements? I choose a molecule Can I pass any symmetry element I like? I mean, I'll choose a rotation or I choose a plane. Can I pass it from anywhere I like? I'll take a plane, I'll try to pass it from here, or I'll take a plane, I'll try to pass it from here, I'll try to pass it from here. Can I do it? The answer is no, because there are little guidelines. This is just for our understanding. What are the guidelines? That guidelines say, once I've given you a molecule, first prerequisite is, once a molecule has been given, the minimum knowledge that any student should have is the geometry, or you may say what is the structure. You should be having an idea about the geometry or the structure of that particular molecule. Without knowing the geometry or the structure of the molecule, you cannot operate any symmetry element over it, because you will end up with a wrong answer. Example, I ask you to say what are the symmetry elements present in water molecule. Then as a student, I will draw this structure. So if I take this geometry and I try to pass the rotational axis, I will get n number of rotational axes. It belongs to infinity. There are infinite number of rotational axes in this. Then definitely I will go wrong. So without the basic knowledge of geometry or the structure, you just cannot operate any symmetry element on a given molecule. Therefore, we say the first prerequisites, the first requirement for passing any symmetry element in a given molecule is, one should have a knowledge of the geometry or the structure of a given molecule. Without that, we cannot proceed. Right. I know what is the structure of water molecule or ammonia given. Then once structure is known, I have drawn the structure. Now I am trying to pass it through the bond, I am trying to pass it from the hydrogen. Again it is not valid. Why it is not valid? We have a second guideline. Center of gravity must be considered. Center of gravity must be considered. So whatever symmetry element that we are passing through, that should pass through a point called as center of gravity. Whatever molecule that you choose, that will have a particular center of gravity. Now if I am trying to pass a rotational axis, that particular rotational axis should pass through the center of gravity. Only then you start operating, only then you start rotating. Okay. So for rotational axis of symmetry, if I try to pass a rotational axis from hydrogen, it is invalid, because the center of gravity, as we know, it is lying with the oxygen. It will not lie with the hydrogens. If I try to hold the molecule with hydrogen, it will not stay, because the center of gravity is lying within the oxygen. So wherever the center of gravity point lies, from that particular point called as center of gravity, all the symmetry elements have to be operated. Okay. Now these are the prerequisites. One should have an idea about the geometry and structure. Second prerequisite is center of gravity must be considered. There is also a third requirement. Orientation of the molecule should also be considered. When I say orientation, in the beginning classes I told you about the coordinates. So once I have given you a molecule, if I am trying to hold it this way, maybe you will not get a rotational axis, because our imagination in the beginning stages is restricted to z, x and y. So this is how we are seeing it, right? For your imagination I am just repeating. So for convention, imagine this as an axis. I am showing a finger, imagine this as an axis. If I show it this way, or you can show it to yourself, if I am showing it this way, this will become z, this is x, this is y, right? And if I show it this way, you can represent it as a plane. Now this become an xz plane, this become a yz plane, and this become a xy plane. So this you have to keep it in your mind, right? Again I am repeating, this is z, x and y. This become xz, yz and xy plane. So whenever I am holding a molecule, we have to hold it in such a way, orientation should be in such a way that it is falling into some coordinate. that will be easy for you. Once you have attained some mastery over the symmetry, then you may hold it any way you like. You may hold it any way you like, still you will be able to imagine the symmetry elements. You can operate the symmetry elements just from your imagination. But in the beginning stages, you have to properly handle it. So orientation must be considered. In what way am I orienting it? I am orienting it this way. Now this becomes Z, this becomes X, this becomes Y. Then try to pass a rotational axis from Y, rotated by 180, it is not equivalent. Then pass it from X, rotated by some angle 180 or 200 or any other angle, you are not getting any equivalent configuration. But when I am passing it from Z, and as I rotate by 90, not getting 180, I am getting an equivalent configuration. So I say that there is a rotational axis when I am passing it from Z axis. For this reason, we are taking along Z. We don't take along Y, we don't take along X, because it will not generate any other rotational axis. Don't take along Y or X, take it only along Z, because along Z we are getting a configuration that is indistinguishable from the original one. Also, don't pass it from hydrogens or the bonds, because it is not the center of gravity. Geometry is not linear for water molecule, it is angular. So these are the prerequisites for performing any symmetry operation after choosing a symmetry element. So with this basics, now we will start operating it over the water molecule. This is along Z, convention I am drawing it here. X towards you, Y towards your right hand and left, and Z top and bottom. So along Z, I am rotating it. To what angle should I rotate? It should only be a valid rotation, valid operation. And the angle that we have chosen is 180 degree, then you are getting an equivalent configuration. So we calling it as a C2. How did you get that C2? Cn, you don't know the n, 360 degree by, I am rotating it by 180 degree to get a configuration which looks just similar to the original one. Put that angle 360 degree upon 180 degree, that gives you 2, therefore it is a C2 rotational axis. Then once I have done a C2 rotational axis, in the stereographs I have explained you, the position of the atoms will shift. These two hydrogens are identical and these two hydrogens have a linear relation. So since they have a linear relation, you can exchange them by a 180 degree rotation. It is not possible with every molecule, but it is just a common knowledge that whenever two identical atoms are having a linear relation, then they can be exchangeable by a 180 degree rotation, provided the other atoms are symmetric. In this case, we only have an oxygen. Suppose if we had two other atoms which are non-identical, then such a rotation is not valid. But in this case, we only have one oxygen, then these two have a linear relation, rotated by 180 degree, they exchange. After exchanging, you can see 1 and 2, 1 has taken the position of 2. H1, which is towards your right hand side, has moved into your left hand side. So this particular orientation, which is in the plane of the board, they both look alike, but they are not the same, because the position of the hydrogen atoms has changed. For this reason, what we do is we have to rotate it another time. How many times should I rotate? Should I rotate 100 times? The answer is you have to rotate until you get identical configuration. Whenever you get an identical configuration, stop there. Don't rotate further. Theta is again 180 degree, so this is again a C2. C2 for the first time, this is a C2 for the second time. So as I rotate by a clockwise manner, 1 will shift to the position of 2, Now you need not rotate it further, because the first one and the last one, they are just looking the same. The first one we call it as original configuration. The second one is equivalent configuration, and the third one, which is just looking the same as that of the original one, you call it as identical configuration. Which pair is identical? If we ask, 1 and 3, they are identical pairs. 1 and 2 are equivalent pairs. 2 and 3 are equivalent. 1 and 2 are not the same, they are similar. So 1 and 2 is equivalent pair. 2 and 3 is equivalent pair, but 1 and 3 is an identical pair. Whatever molecule you choose, you will get only one pair which is identical. Remaining every other pair will be equivalent. Okay. So this is where we end up by taking a water molecule. Now what we will do is, we will just take a reference. What is the importance of this reference point, you will come to know as we move to further classes. So that reference point I am telling you is a plus, or you may take it as an arrow. Once I have chosen this arrow is pointing towards your right hand side. So as I am rotating, you can just watch this. Suppose if this is the arrow which is pointing towards your right hand side, as I rotate to 180 degree, now that is moving towards your left hand side. So this is H1, this is also H1, but the position of the arrow is differing. H1 position of the arrow is differing. For that reason, the first one and the second one are not identical. Okay, so this is how I am showing it. This is moved, and I rotate it by another 180. Again, it is coming to its original position. It is better for any student to choose a particular reference point, and whether that reference point is repeating itself or not, you have to check. In this case, that reference point was moving away, now it has repeated itself. So that is your identical configuration. Okay. Here also I will give you one more reference point. It is little bit difficult in your beginning classes, but slowly you try to understand. Once I give you some molecule, this is for your understanding purpose. Just imagine that this is the molecule oriented in a one particular plane. This particular plane we are calling it as a YZ. If I hold it this way, XZ. If I hold it this way, this is XY plane. So if I am holding it in the plane of the board or on the plane of the paper as you draw it, this is a YZ plane. Now in this YZ plane, one half is facing towards you, one half is away from you. Okay. So for our understanding, or for your understanding, whichever half is facing towards you, you just label it as plus, and whichever half is away from you, we will try to label it as minus, only for our understanding. Okay. Whichever half is facing towards you, you label it as plus, and whichever half is away from you, you label it as minus. Now once I do this, what happens is, within this hydrogen there is one half which is plus, another half which is minus, right? Now if this is plus half, this is a minus half. What is happening to this plus half? As I rotate by 180, it is moving away from you. So that place is becoming minus. It means whichever half was facing towards you, as you rotate, for that H1, it is moving away from you. This will have a greater importance when we discuss plane. Maybe here you may not find it a great important, but whenever we discuss plane, that will become more important reference point. So for our reference, as I said, whichever half is facing towards you, you just label it as plus, plus and plus for our understanding purpose. And whichever half is away from you, you just label it as minus. So as I rotate, you can see H1, which is towards your right hand side, plus is facing towards you. As I rotate, H1 is moving towards your left hand side, and plus is moving into minus. So that reference point, if I take it here, plus as I rotate is moving into opposite direction, and which half is towards you? Whichever was away, that is coming towards you. Okay, so plus is moving away, it is becoming minus. As I rotate by another 180 degree, slowly that minus will come towards you. So that reference point which was in plus, suppose if this is plus, as I rotate to 180, now it is becoming minus. Now again I rotate it to 180, it is becoming plus. Now this is an identical configuration. Once it is like minus, it is equivalent configuration. So this is how we have to take a reference point as the beginner. Once you are aware of all these reference points, how they are able to rotate, how the phases are moving, then every time you need not put any reference point. Simply you put the atoms, try to shift the position of the atoms, that will be more than enough. But as a beginner, you should be aware of all these reference points. So this is with respect to water molecule, right? So what we have learned till now is, once we have chosen the rotational axis of symmetry, from the beginning classes, you have to check how the coordinates are present, and as I pass the rotational axis through these coordinates, how are these coordinates exchanging themselves with the opposite phases? Is every coordinate exchanging or only a particular coordinate exchanging? That we have seen in the previous classes. Then we have taken 5 symmetry elements. From that 5 symmetry elements, each and every symmetry element has to be dealt separately. We have started with rotational axis of symmetry. In this rotational axis of symmetry, we discussed about Cn, and what is n means, it is referring to periodicity or fold. We got it from this simple formula 360 degree upon theta, where theta is the angle of rotation. To what degree you have to rotate to get a configuration which is indistinguishable from the original one. From that we got n. We have generated various stereographs, and to understand those stereographs we have taken one of the simplest examples, water molecule. So it is not just water molecule, whatever molecule that you choose, you have to pass the rotational axis from a point called as center of gravity. Geometry must be known. If you don't have a knowledge of geometry, it is very difficult for you to pass any symmetry element and do any particular symmetry operation. So as I said in the prerequisites, the geometry of the molecule should be known, center of gravity point should be identified, then proper orientation has to be done. After that you try to perform the symmetry element. So this is about the water molecule. In the next classes we will take up more examples, and then we will try to enumerate the rotational axis of symmetry in it. బయటకు వెళ్ళండి, ఇది లాంగ్ అయింది క్లాస్, గంటం పావు అయింది.